Today we are continue to talk about large language models like Llama 3, Mistral, and DeepSeek. But before that, let's talk about homework. This is homework 3, which will be published on E3. This homework involved with using Ollama, which is a software that can run large language model locally. And this homework invite you to run Ollama to run several different large language models and compare their performance. So first, this is a website of Ollama, and you can find many different models that are available to Ollama. For example, this is GRPO, and from this list, you can click here, view all. You will see all the different versions, like 4 billion parameter, 27 billion parameter, 1 billion parameter. So all of them have different size. And the IT means they are instruction tuned. So sometimes they will have both version of the IT version or non-IT version, but in this case they are all IT version. Even if you see like this 4B or 12B, they are in fact just an alias of the following more detailed, the models with more detailed name. And you can see this name which has a label or a tag for the quantization. For example, FP16 means this is a float point of 16 bits, and for QA underscore 0 is a quantization for a model to become 8-bit. And there are also like 4 bits quantization model. Sometimes you will see like Q4KS or other alphabet after this Q4. I'm invited to read this article to discuss what all these things are represents, what is the KM or Q4 QA means. Because this is not directly related to the topic, which is generative AI that we are talking about. So I'm not going to detail, but because the quantization model use a lot when we using a large size model like language models or diffusion models. So it would be ideal if you can understand what all this quantization works. They are not too difficult. They are follow pretty simple formulas. And another way to understand or to kind of getting a feeling of this quantization is to actually run different version of the weights. So this is this homework about. So in this homework we are asking you to actually run the two kind of different model, like the I should fix this typo. Okay, this is GRPO 4B IT and GRPO 1B IT. Because probably I will write something I compare, and this appears right here. This is actually GRPO 1B. Okay, so choose two different models so that you can compare different model, the performance of different models of different hyperparameters, like different number of parameters. Like this model has 4 billion parameters, and this one has only 1 billion. So in theory, maybe we will expect that a larger model will perform better but slower. But whether this is true, you should try it on by yourself, and it is quite easy to try. So you can, for example, use these two models. If it is your choice to choose which model used in this homework, but you will have to try two different models, which ideally they have different size. But optionally, you can choose two different family of models that has comparable size. Maybe you can compare like Llama 2 to Llama 3, or Gemma to like a Gemma 9B to like Llama 7B or 8B models. It is your choice. There are two different aspects that you can compare these models. One is from the quality, and the other is for performance. For the quality wise, this is not in the scope of this homework because you can do it by yourself, but I'm not asking you to write like a simple essay or like an article to compare the qualities of the generative text for different model. So I'm only asking you to compare the speed of these two different models. Okay, anyway, there are 4 billion parameters. In this case, we have a Gemma 3 4B and the Gemma 3 1B. They have different size. And for each of these models, choose 3 different quantization weights. For example, like FP16, Q4KM, or QA0. That is what you can actually find on this page. Of course, there are also other models like 12 billion parameter models or 27 billion parameter models. But because some people may have some limitation of their hardware, so I was choosing the 2 smallest models so that you can try on relatively low-end hardware. Okay, so for these 3 different weights, and we have 2 different kind of models. So we already have a combination of 6 different cases, and also try listing on GPU and CPU to see what's the difference. Okay, so you have 12 different combinations, 12 different configurations. Just make a table to show what is the to demonstrate what is the main the primary factor to affect the speed of the model. Thus, 2 different models with similar parameters, number of parameters, performance like comparable, or is the bit is the primary factor to affect the speed, or maybe that like even if you have a 4B model and even if you have a 4-bit quantization, maybe it is even slower, still slower than a 1 billion model, which run in floating 16-bit floating numbers. So that's the purpose of this homework. Try differences and get a feeling of what affect the speed of the inference of a prediction. You can design your prompt because you need a prompt to actually test the speed. So in Ollama, if you use some configuration or like if you were running the command line interface, it will have it has a like a verbose argument verbose, so that you can actually see the tokens per second, the speed of the generation. It also shows a lot more information, like how many tokens it generated, or like how many tokens are in the prompt and how many tokens it generated. But anyway, we are mainly focused on the speed, which you can see on here. like the prompt eval rate and the evaluation rate. The reason that we have two different things is the model can handle the prompt and the generative thing differently. As we mentioned before, when GP-like model or the modern large language model generate text, they are generated in an autoregressive way. So it pretty much generates the tokens one by one. However, when they runs on the prompt, they can run them at once. So they are differently. So the prompt evaluation rate and the evaluation rate are different. So you will see these two differences, and the difference should be really huge. So why they different so much different? They are same models and they are all handling tokens. Okay, so that's another exercise that you should figure out. And so you should design your own prompt, because the length of the prompt also is a factor of that affect the speed. So if you and your friend trying to do this homework and you are feeding the very different kind of prompt, maybe your result may be different. So anyway, this is your choice. You can choose different prompt and different models weights and see the result. But the idea is that to familiar with different models and Olama and get a feeling of the quantization, how quantization and the number of parameters affect the generation speed. Okay, you should submit your work in a document format. Ideally, I'm expecting with some kind of like a table or some graph. If you have some graph, that would be better, but that's optional. You should at least provide the data in a table format. Also, for these all 12 experiments, show the screenshot. You don't have to show everything, but show something crucial, so that we can actually see how you run it. And for the GPU part, if you don't have a GPU, you can use the free Colab GPU to run it. The free Colab GPU actually is, I think it's T4, and it has a 16 gigabytes memory on the GPU. So that's quite more than enough GPU that you can run. For example, this 4B or 1B model. Okay, so that's the homework, and let us continue with the introduction to the models. Okay, so last week we talked about Llama 1 and Llama 2, and there's also Llama 3. I can also talk about Llama 4, but Llama 4 is a little bit different. I will talk a little bit about it, but not fully about it. So what's the difference of Llama 3? Mostly the data. Okay, compared to pre-version of Llama, the data is improved in quantity and quality. So like you can see that they pre-trained Llama 3 on a corpus of 15 tera multi-language tokens, compared to only 1.2 tokens for Llama 2. So that's one of the big differences. And the other difference is that they are using more computation power to train it. Also, in this table show the Llama 3, Llama 3.1. There are also Llama 3.2 and Llama 3.3. For Llama 3.2, it is actually a multimodal model, so it can handle image as input. We will talk about different ways to handle image for large language model in in following weeks. And also they are using certain training methods, including like we have already seen the supervised fine tuning, which is the original or the baseline instruction tuning method, and like Llama 2, they were using the rejection sampling, and also they are using a thing called the direct preference optimization, also known as DPO. This can be viewed as a kind of variation or improvement to the reinforced learning with human feedback. So we're talking about this type of things right now. Okay, so let's go to here. So let's use the previous slides right here. So after RLHF, we were talking about some variance that is considered to be the improvement to the RLHF. Okay, so we have already covered the RLHF, which is basically try to train the language models by using reinforced learning method, so that we don't have we can solve the issue that is we can actually use the output of the language model to train it. As we can see, as we said before, because we are training it in a more like an autoregressive way. If we are training it in an autoregressive way, sometimes it will have some like the bias. Let's go to the page. When we talk about say it is repeating itself. Okay, exposure bias which we discussed before, because the difference between the training and the generation. So one way to actually kind of solve this issue is, okay, we do not train it this way. Whenever it is generating an output, we are using a reward function to judge whether or not this output is good. The gold standard is human response, but human is too expensive, so the RLHF replace the human by still human has to label some input output, but we can train a model that mimic humans judgment behavior. So that is there will be a reward model. Also recall, there will be a reward model. And also there's some treatment like using comparison or something like that. Okay, and they are using a reinforced learning algorithm called the PPO, which can be considered one of the best reinforced learning algorithm available. That's why they chose the PPO. Okay, so there's also RLAIF. So you may wonder, why do we actually use RLAIF? Of course, this means we replace human by AI. Because RLHF, the H stands for human, and here RLF keep the same, but the H is replaced by AI. So you may wonder, why should we do that? Because we have already replaced the human by a reward model, and the reward model is an AI, right? The difference is that you can see that in this in this illustration. So the button process is the original IHF policy, IHF things. The above is the RLAI pipeline. You can see that the only difference is that here we have a human do the rating. That is the only part that human participate in the ILHF pipeline. After they train the reward model, they are replacing the reward is actually given by a trained reward model. Here, they actually replace this human being in a human process by an off-the-shelf LLM. So that's it. The original or the base AIF is that, okay, why not just eliminate the human entirely? We don't want the human to label the things. We just ask the large language model to do a rating. And after they do a rating, we do the same. We still train a reward model to give the reward, to give the feedback. So you may wonder, why bother? Because if you have already has a large language model that can do a rating, why bother to actually train a reward model? Because you already can do everything automatically. You can already do a rating automatically. The reason is that the large language model used by right here is supposed to be much slower. So this reward model is expected to be much faster because when we train the reinforcement learning, it requires a lot of simulation process to do a lot of trial before we can actually train the model. So a faster, smaller model would be beneficial. So that's why they first use a large language model to actually distill to a reward model. You can actually say that because we are distillation use do the knowledge from large language model to train a small model. So that's the idea. Okay, so that's. But the thing is, we still think maybe human is supposed to be better at this job. Does LLM can kind of catch up to human being in this task, which is kind of doubtful because I think before anybody do that, I would say that there will be like a 20% chance to be success, but in fact they are success. They success at least in some scenario. You can see that the RLHF is still better than RLAIF, but not by much. So the winning rate is slightly different. Let me explain this graph. They are actually ask the RLAIF to fight with a model that trained by using only SFT, and the blue number indicate when they compare an RLHF with SFT, what is the winning rate of RLHF? The process is like they are providing by giving a random prompt from maybe from a data set or so. They give the same prompt to RLHF model and the same thing to SFT model and generated the things to two different texts, and they ask a judge to judge which one is better. The judge, similarly, the judge can be human, which is like the LMSYS arena. So they have an interface to ask human to judge who wins. And in some benchmark, they are using a large language model instead, maybe like a GPT-4 or other models. But anyway, in this scenario, they are comparing our AIF to our HF against SFT model, and it seems that they are not different that much, which is like the case that I would say I would predict for the 20% case, but they actually managed to make RLAIF to catch up with RLHF, but they are doing a lot of they are using a lot of different technique to apply on their RLAIF. So, for example, they are using a different like prompt and the scenes and the scoring method to do that. So they have different choice. I guess maybe they are actually doing it pretty well, because maybe if you are doing the same, if you have the same idea of RLIF, but using a different variation, maybe the performance won't be that good like them. But this is just merely a guess, so I think that they still need some experiment to verify that. But the key point, the main point is that the result is very close, and they actually show some work to actually improve the result. So I think that this is very interesting work. But still, I mean, they can see a lot of differences. One of the things is interesting, so at least here, it is like a position bias. Because the older of the candidate, I mean, when we generate two texts, like in this process, we generate one text, one response, and two response, and we are asking the judge, the human or either human in ILHF or large language model in ILAIF. We ask them to judge which one is better. Okay. So in this case, if the judge is a large language model, it will have a preference for these two candidates based on their order. This phenomenon has been observed. Maybe the first one, maybe the second one. And in fact, human being has the similar tend. Like if we were asking to choose one thing or two things from a list of candidates, the order will affect the choice of human being as well. But I think in this case, maybe not that much, because we only have two candidates. But we already know that for large language model, even we only have two candidates, the order really matter. So in order to solve this issue, okay, and then let's say it's a more pronounced with a smaller size of large language model. Okay, so in order to do that, they actually ask the labeler to do it twice. The first time maybe R1, R2, and then the second time they switch the two models. I mean the two response. So after it's too wrong, they kind of average the score. So to make them be more fair. also tried whether or not using the chain of thought reasoning, and they found that chain of thought reasoning performs a bit better. So this is they are trying to use a chain of thought, like COT is chain of thought. You can see that with the COT it is getting better. Okay, that is the first part of the interesting part of AIF. They achieve performance so that the performance is very close to HF, and they provide a list of techniques they used and the variation they used in their implementation, and all of them are interesting and very reasonable. But the thing is, because like we mentioned before, the reason that for IIHF to train a real model is that a human being is too expensive, and can consider is not automatic process. But when you try to use the large language model as a labeler, it is already an automatic ratings process. So why not use it directly? If you think the larger model is too expensive, maybe you can use a smaller off-the-shelf large language model, so to increase speed, or maybe we can scale up to increase speed. So this is called the direct RLAIF. Similar thing, but they are using, they don't have to train the reward model. They are using the labeling process to give a reward directly. So it shows that direct IAIF is still working, can compare to other things like distilled IAIF, or like when they fight against each other, the direct IAIF is still getting better compared to the original one, which is called the distilled IAIF. Okay, another famous way to do to kind of simplify RLHF is called DPO. The name kind of like PPO, but still it is direct. The keyword is direct. So how does the DPO do? So first, it also compared to RLHF. The reinforced learning from human feedback do things like this one. We have a preference and we have a reward model, and the reward model give the label reward, and this policy, okay, go back. So this is the general sentence, and the reward model give a reward. So this is a whole like a reinforced learning training process. However, like IOAF, like direct IOAF, they are trying to eliminate the need of a reward model by using, you can see that basically all the things like a reward model, which is try to mimic human labeler, but still everything that the reward model knows is lies on the training data. So why not just using a training data directly to train our model? Because every information is right here. So they're using some mathematical formula to simplify the whole thing. The key idea of DPO is, since the whole process is just learning things from this data, why not just, so they try to use mathematical to analyze the whole process to streamline and simplify the things. Okay, the key point is that in the IL fine-tuning phase, they can use they're trying to optimize this formula, and by assuming something, or there are some theoretical model of the best solution of things, they can actually solve this formula by this guy. This one is the solution, except this guy is very expensive. To compute this guy is very expensive. This is like what we have already seen on the VAE, right? Also the part of VAE is when we discuss the VAE, we are talking about that the motivation of why VAE is necessary. We will see that to compute the likelihood, there is also a term like this one. The normalized term is difficult to compute because curse of dimensionality. So this is similar case, and we can use similar method to solve it. We use a log right here. We take a log. So this one becomes irrelevant when we try to do the optimization. We can consider only this part. And by using a theoretical model called the Bradley-Terry model, this one is a theory. Okay, this is not the exact model, but it's a common use theoretical framework to analyze, to do mathematical derivation on reinforcement learning things. They use this Bradley-Terry model to simplify. So they got this solution. So finally, so we can get the LP, the DPO loss. So basically, the whole thing is just to streamline and simplify that everything based on the Bradley-Terry model. Bradley-Terry model is in fact very similar to softmax. They have actually, they do simplify some assumptions, but they are very similar to softmax. And since we are using softmax most of the time, so this may not be that bad. And even if we are not using the softmax, it is close enough. And widely used. Okay, so the basic idea is that trying to simplify all the things. First, we observe that although we have different motivation, like this one should be, this part is reinforcement learning, and this one is try to mimic human behavior. But after all, the whole process is just training on this training data. So why not just simplify everything to find some certain solution? Because reinforcement learning is just too kind of tricky to train and require a lot of computational power. So we use the power of mathematics to simplify the whole process, to find the solution by assuming something. And so in fact, in this setting, we can simplify to the whole thing to train on the training data with this loss. And you can see that in here, we have this pi means the policy. Pi ref means the reference model, like the original large language model that has been already trained by the SFT. So we have a model. Usually when we train these reinforcement things, we have already an instruction tuning model, and we want to refine it to more align to human preference. And that model trained by SFT is called pi ref, and the pi theta is the model that we are trying to actually train. the actual model that is in training. So basically, it says that okay, we have two output. One is YW, which is winning, and YL is losing. Recall that the policy itself is by given any prompt or any input, it will generate some text, response 1 and response 2. And one is the winning response, and the other one is losing or less less preferred response. So basically, we increasing the probability of generating the winning one and decrease the probability of generating the losing one. So that is this formula about. The thing you need to notice is that we still have a reference model, reference policy, but we don't have a reward model. There's no reward model at all. They only train everything on the data set itself. Okay, so this is explanation like what I was saying. The thing I didn't explain is probably just this guy. Okay, anyway, the winning rate of DPO is pretty good in some cases, and it can be trained more efficiently. There are a lot of improvement among the DPO also. Because DPO is so powerful, there are a lot of different variations that try to improve DPO. One of them is called the simple, which is also a very interesting algorithm to do that. So this is the formula of DPO, and this is the simple. They are also using similar way to actually to derive the formula with slightly different approach and assumptions. But the key point is here. You can see that they don't have reward model, or just like the improvement on overall DPO. All of them won't have a reward model. But another thing is it doesn't even have a reference model. You can see that it doesn't even have a reference model. The reason that the reference model exists in a lot of like DPO like algorithm is because although we were saying that okay, it is everything can be streamlined and equivalent to this guy, but the thing is the reward, the dataset itself is trained on the reference model, original model, like if you remember the process of how this guy is generated, we are using first we have a SFT model, right? Instruction tuning SFT model, and we let it to generate different response, and we ask human laborer, if we are working with IOHF, we're asking human laborer to pick which one is better. But every response right here is generated by SFT, not by unlike the real IOHF here. These responses are generated by the running model, the training model. The model is being trained. So this one is called online training because every time it is generate something, the real reward is coming from the output from the model that is actually being trained. Unlike this one, although we're kind of saying they are kind of equivalent, but the thing is still they are training on the preference data, which is these two outputs is generated by the original training data, and in the training data, all these outputs are generated by the reference model. So this is called the offline. They are training on something, although we finally get something like a DPO formula, but they are actually training on something that is not the output of the living model or the working model. The model is being trained, unlike this one. Although this is just an approximation, but still, every output is generated by this leaving the training policy. So that's the whole difference. So because of this is offline, so we cannot, usually we do not want it to be too far from the original reference model. If it is too far, the new model here, if it is too far from the reference policy, then maybe this data is not that useful because they are totally different models. So these things may not be that, the domain of this guy is totally different because the policy is different. So the information contained here is not that relevant to the new model because the reference model and the training model are too far away. So we usually want to have certain term to allow that the new model, the training model and the reference model to be not too far away. So that's why we usually will have some certain thing like you can see that we have an origin that here they cannot be too different. The policy here and the reference model cannot be too different. So you will always have a reference model. But the thing is DPO doesn't have this thing. A simple doesn't have this thing. Simple does not require a reference model. So it sometimes which can be beneficial. And it also has a pretty good performance defeating the simple defeating the DPO. And actually in this paper has an interesting result that says that there are two interesting results. One is saying that when they apply to GRPO2, it get much better score than Llama 3, which indicate that it might be that the GRPO2 model is more suitable for fine-tuning than Llama 3 model. Although GRPO2 and Llama 3 does not perform that different, but when we consider to be fine-tuning, maybe GRPO2 is more suitable for Llama 3. So that's one observation. Although we already have GRPO3 right now, we have a Llama 4 right now. But the take point is that some model may be easier to fine-tuning than another. And another interesting observation of this paper is that a lot of large enhancement of DPO is not that good. You can see that in this paper, in this table. DPO, all of these are kind of a large enhanced version of DPO, but in fact, when the author of Simple try to reproduce the result on several datasets, it seems that they does not defeat DPO by much. Also, in this paper you can see, in this table you can see that Simple is not the first enhancement of the DPO that does not require reference model. There are I forgot which one, but some of them does not require the reference model. Okay. So back to here. Here they are using the Llama 3 use SFT, rejection, sampling, and the DPO to train it. instead of using IHL. So here's the result, is pretty good compared to others. And they also have something like vision adapter training, speech adapter training, but not in so mostly I will talk about the multimodal model, which will including the how the Llama 3.2 works. Okay, so the next topic is the mixture of experts. This is a paper of Mistral, which is one of the famous famous models for the MoE, the mixture of experts. Here is a simple illustration. So I'm using the Hugging Face article, the mixture of experts explained. You can see the outline and the context of how this technique evolved. So first, one thing is called the sparse MoE layers, which is used to replace feed-forward network, kind of like the gated linear unit. People always try to replace the FLN by other kind of things. So MoE layer have a certain number of experts, but it is just a name. You can consider there are several parts of smaller feed-forward network. We have a different feed-forward network. I can see in this. The idea of mixture of experts, at least on large language model, is not too difficult. Is first we have different version of the feed-forward network, and the idea is just choose a few of them, or maybe we can use a weighted sum of their output as our final output, and then that's it. So if we only choose like a few of them, like 2 or 3 of them, you can imagine that the thing is that the intuitive idea is that everyone has a different, every expert has a different area of expertise. So we use a router. You can imagine that router is just output something like softmax or something, like kind of like a get, like the GLU get things. So we are just getting things. Okay, so the input, we route this input into its expert, and we choose several of them, some of them, and kind of like gating. We do the summation on the selected expert and do the output. And every expert is simply a FLN. So it all depends on the router. How do you choose which expert to be used? And also, there are a lot of different considerations on the training, which we will introduce in a while. In a moment, okay. So the original, the router is simply a get network router, kind of like a gated, the gate in a GLU or in LCM. Okay, so this one is an illustration of a switch transformer encoder. Okay, so they actually has two sequence of input, and these two input they choose different expert and choose they output different things. Okay, so this is the graph right here, and this replace the this is switch. We're still talking about switch FFN. Switching FFN is actually one of the kind of a mixture of expert. There are different mixture of expert. So this is one thing that works. So the idea of the mixture of expert can go back to very early. I mean, the idea of like we use some expert to handle some situation, kind of like a decision tree. So you can imagine this one, people is going to think about this one and this approach. But originally, I mean, if you really think about the original attempt might be work on the whole system. Like, okay, when we encounter a problem, we will kind of dispatch this problem to the given expert. So suppose maybe you have like two large language model, and maybe like Gemma is more suitable for like answering question about human chat, and maybe the cloud is more good to do the coding. So right now the best coding model is Gemma 2.5 Pro, but I mean for a very long time, cloud is sort of performs very well on the coding. So I'm just giving you an example. So suppose you have two models. One is good for chatting, one is good for like coding, like cloud, and another one is good for like maybe mathematics or doing proof. So when you get a request, you simply classify this thing to be, okay, is this a coding problem, is this a mathematical problem, or this is just a chat, and you just branch these things to the given model. So that is a system-wise mixture of expert. However, in the large language model, like a switch transformer, currently when we talk about mixture of MoE models or like MoE LLM, we are pretty much using the MoE as a layer here to replace every or replace a lot of, maybe not every, maybe every two FFN, but they are used to use as layers. Okay. So another architecture is Google's called shard or thing, or like so they, since the switch transformer, they have improved a lot of different, like this one, they have a lot of different experts, and you usually get to choose some of them. Okay, the sparsity, you remember that we call it the sparse mixture of expert. The sparsity means that we only pick certain part, I mean, pick some of the expert, not all the expert. In this way, we can make the system the model more efficient. So the sparsity comes from the characteristic that for all input allows that to only run some part of in the whole system. Okay, so how can we actually do that? So for the gating itself is more like can be a softmax things. Mostly this is the typical case. There will be other variations, but typically, okay, we are using a softmax. But softmax Although ideally Somax is still concentrated on a small number of the element, but still a lot of different elements will still have a small weight. So how do we change this one to more like more sparse things? Okay, they use one of the things use a noisy top K gating. So this one will make it trainable, but when doing the actual inference, they just keep a they only keep only top K elements, but by adding a noise, they can make it still able to train. If you are not using a noise, they are not going to be trained well because only the top K element is going to be have a back propagation gradient, non-zero gradient. So by adding noise, it makes it possible to be trained. But by keeping only a top K, it can make it sparse. Okay, another thing is why not just top 1 instead of we need top K? So this is a conjecture that the routing to more than one expert was needed to have a get learn how to route to different experts. So at least two experts um, had to do that, but the switch transformer section refines this decision. This is just a kind of intuitive way of thinking, but seems to be very reasonable. But as always, this may not be the truth. It requires experiments to verify it. Here also explain why we need noise and there's a terminology called load balance. So like we say, if you don't add the noise, it will concentrate on, a lot of non-top K part will not have will have no chance to get the gradient. So ideally we wish, since we have a large number of experts, we wish every expert to have certain chance to contribute their expertise. So that's called the load balancing. There are different ways to solving or trying to solve the load balancing problem. The terminology is load balancing. So the noise, without noise, like we mentioned before, it will concentrate on a few experts. So you only train those experts, and those experts become strong. So they are keep getting better and better. And for all other experts, they are not getting trained, so there will no chance to be top K. So they will have less chance to be trained. Also, this is called the self-reinforced manner to favor some expert train to quicker and select more. And okay, also Google exploring with G-Shard replace every other FFN with MoE layer using top 2 gating, like we say the top K gating. They do it in both encoder and decoder. Mistral is also using G-Shard, but kind of like G-Shard, except they replace every FFN, not every other FFN. Okay, the switch transformer get huge success to 2048 experts. And for the Mistral, it just like in G-Shard, but they replace FFN with every FFN with all layers. The transformers I mean, this one is for the switch transformer. The switch transformer have a proposed switch transformer layer that receive two inputs, two different, like the two stream of things. Do we have the other? Yeah, this is what it means, that two different tokens. And has 4 experts. Kind of like this one. I don't have to go back to that illustration. We already have this one in the next slide. So contrary to the initial idea, using at least 2 expert switch transformer use a simplified single expert strategy. So every time it choose only one expert, only, not 2, just 1. And it still works pretty okay. And it also explores the concept of expert capacity. Like the purpose of this one is to do the load balancing. So it has like a credit or capacity balance for each expert. So if the one expert is not used too often, it will increase the chance for that expert to be used. So it's called expert capacity here. So that is the formula. Okay. For the this is a Mistral. They use top two, and the softmax right here, and the switch GLU. Okay, another interesting architecture is DeepSeek V2, and we are going to talk about DeepSeek R1 also. There are 2 key points of DeepSeek V2. I mean, aside from the training, data handling, or reinforced learning, the architecture has 2 contributions. One is the multi-latent attention, and the other is the DeepSeek mixture of expert. Also, there are 2 contributions of the DeepSeek. One is DeepSeek MoE, and the other is multi-head latent attention. The DeepSeek MoE. Let's first talk about MLM. The idea is to compress the size to make the key value generation more efficient. So instead of generate the key value directly, they first generate a latent shared by the key and the value, and use this shared latent to generate key and the value right here. Or the similar thing for the queue. And because of this way, and when they do to find the most, to compute the attention map, they can be simplified to a more efficient way to do that, and they can save in the memory. So this guy is they use a low rank key value joint compression, so kind of like LoRa. They take a similar idea to compressing the data, and right here you can say that there are some by doing the computation, you can see that a lot of steps can be simplified to make it much more efficient. So they don't even have to compute the key and the values out for attention. So although theoretically they are doing this way, but in practice they don't even have to compute the keys and the values. They can already get the attention. For the they are mostly for the key and the value, but for to make it more efficient, they also, I mean, they are not, it's not compressing, but it can still make it more efficient. So they do the same for Q also. They are mostly doing that for KV. The motivation is for to compressing KV. This is a key idea. This does not work right here, but it will make things more efficient. So they do a similar thing. However, they still want to use rope, rotatory position embedding, but rope is incompatible with low rank KV compression. The thing is that you can still do that, but the benefit is going to be gone. The benefit is this guy, that they do not need to compute the key and the barrels out of attention. So the workaround is they decouple the rope. So that's why they need this guy. This one is the low rank compression, but this guy is used to decouple for the rope, and they have this guy too. Okay. This is not very clear, but let me try it again. Okay, it seems to work. Okay, so we have already been to DeepSeek, right? Okay, so this is a compute. So you may see that this is more complicated than the original, like multi-head attention or even with the group attention. Like, but so it is not that immediately see how efficient it is, but after they actually compute the token, you can see that it is actually cheaper, faster, and the capability of it is really good. The DeepSeek MoE, so that is for the MLA, multi-head latent attention. And another contribution is the DeepSeek MoE. It has two key ideas: segment in expert into finer granularities for higher expert specialization and more accurate knowledge acquisition, and isolating some shared expert for mitigating knowledge redundancy among route expert. So basically, they have two different types of expert. One is shared expert, and the other is segmenting expert. So basically, you can see this one. Some experts are always used, that is shared expert, and someone is kind of routed by the gate. Also, that's the idea. Part of them are always on, and part of them are like kind of like other traditional mixture of expert. Then they still use like a top K right here, and they also use a lot of different technique like device limited routing, auxiliary loss for load balance. They do a lot of different tricks for load balance and to make it more efficient. And another thing is they are introducing GRPO. Like the name suggests, it is also another preference optimization. We can directly read the all of these guys, like the simple DPO, they all has certain motivation and some of the calculations to derive their formula. But you can always read this type of things, I mean the loss function, to actually get a sense of why this should work. And first of all, you can observe that this one also has a pi old. You can see that pi old right here. The old means we still got a reference model. We're still getting a reference model. So it is kind of like a DPO things. The key point of the GRPO is the thing G means it has a group. So first we see the A right here. Suppose we have a group of a response like R1, R2, R2, RG, different response. The A is the advantage of some of these, for each of the response, we can compute the advantage of this response among the group. Basically, we simply do the standardization to divide by the standard deviation of this reward and Ri minus the mean. So this is standard deviation. So we have a group of different reward. We can compute the advantage AI right here. And all this kind of thing. First, you can read here. We have a pi ref. Sorry, pi theta odd is not the theta is theta odd, but not pi odd. So I was wrong. The reference model is pi ref. So this part is pretty easy because this means that your pi theta should not be too far away from the pi ref. How about this guy? You can see that it seems to be a very complicated formula, but you can read right here. This Q is from PQ, that is from Q is the query. So you get the query from the data set. You get a query, and the output from the old theta. Your theta is going to be update to a new one. So you get this OI here. Those are those output. Then we need to update the theta to minimize. You can see that this theta is to minimize these things. Okay, so to maximize this thing. Okay, so you can see that this guy is the minima of this guy and the clip of this thing. Although, and they all times AI right here. Although this one seems to be a bit confusing, but basically this is only because they have to consider a lot of different situations. So like maybe AI to be positive or negative things. So in either case, you can see that it is just, most of the time we want it to be like pi theta OI divided by pi theta old and times AI. This is the things we want to compute, and we submit we sum all them together and divide by 1 over g. That is a mean. We want to compute the mean of it. The thing is, we don't want it to be too big or too small. So we do a clip or do clip. So it will be no more than like 1 plus epsilon or 1 minus epsilon. That's it. If it is over these things, we will take the small one of them. So this is just a limit on the scale of these things. So that's it. So basic idea is just this guy, but we want some limitation. So this is the bound of it, and we don't want it to be too small. So it is bounded by this guy. Okay, so this is GRPO. GRPO is getting famous by the DeepSeek R1, but right now we are talking about DeepSeek v2. It is introduced in DeepSeek v2. So why should what is the difference between this GRPO and the DeepSeek R1 GRPO? The formula is the same. The formula is exactly the same, except GRPO is a general algorithm to train reinforcement learning. So they are using different way to do a training. Here they're still using RLHF, but in DeepSeek R1, they have an environment that can automatically give you the reward without the model. So here they still got a reward model, and for DeepSeek R1, the reward is generated by by algorithm. So what's the difference between DeepSeek v3 and v2 that we just mentioned? Not much. The architecture is the same. I mean, architecture-wise, they are exactly the same, but they have a lot of different handling on the data preparation things. For example, it has a distillation from DeepSeek R1, and it has several rewarding and multi-token prediction evaluation. So it was a reading, but for architecture, most of the interesting part, like even with GRPO or like DeepSeek MoE and MLA, multi-head latent attention, are all introduced in DeepSeek v2, not in v3. And v3 also uses them as well. Okay, finally, let's talk about DeepSeek R1. The first is DeepSeek R10. So it used the still use a GRPO. The only difference is you can see the formula is exactly the same. The only difference is they are doing it on a data set so that it will has a way to verify whether or not the answer is correct. So they are all limited in a subset of the problems that their answer can be verifiable. So that's a key point. Because the answer can be verifiable, you don't need to train a reward model if we are only focusing on the correctness of the answer. We simply check the answer. Sometimes it is impossible to check or difficult to check the answer. So we need a human to judge. But DeepSeek R10 do another approach. They limit the everything to a verifiable problem only. So that's a difference. So in this case, because the answer is verifiable. We only need to ask the model to output to a given format so that we can easily to check the answer. And we're only focusing on the problem that has a clear and easy to judge answer. Okay, so here is a prompt that to train the DeepSeek R10. For reward modeling, it get two different kind of reward. The first is the accuracy reward. So if the answer is correct, it will get some reward. Otherwise, it won't. But also there is a format reward because we're asking the model to generate something that we can easily verifiable. So we are giving it a format. So it has to follow the format. Okay, so for about format, you can see this example prompt. Basically, this is kind of become a standard that the chain of thought is in sync text, and the answer should be put in the answer text. But there's no way to actually verify the syncing process is correct or not. It doesn't matter. It just ask the model to give the model some time to actually sync the problem. We're not verify or checking whether or not it is syncing correctly. We only check it has this format and the answer is whether the answer is correct. Also, it has two kind of different reward. It turns out this, at least it states that the result is very good. So DeepSeek R10 achieved very high score. Consider it is compared with OpenAI's O1 model, which is much slower and larger. Has similar comparable score. And here is the training step, kind of like a reinforcement, because DeepSeek R10 is actually a true kind of a true reinforced learning, like very like the IHF, but IHF the reward function is simulated. Here they are using more given the reward more directly, and also they observe that the syncing length is getting longer and longer, which indicate that DeepSeek R10 is in fact using the sync tag, syncs between sync tag to actually do the syncing. And they also observe a very famous thing called the aha moment, kind of nice one, to indicate similarly that the model can actually correct itself to sync in a different direction. This is become the aha moment is become kind of famous characteristic to DeepSeek R1. But some observe that the original model even before the training, it already can sometimes has an aha moment. So this is kind of arguable, and this is just one case. So this is I think this is something that you can take a eye on, but it doesn't has a quantity measure to it. So just you know that there's something like this one. Okay, because we did what is the drawback of a DeepSeek R10? Because we didn't do anything to the syncing process. So the syncing process, as a result, is not readable. So it has a thinking process. Sometimes it's mixed up with different language. Sometimes it's just very difficult to understand. And also because of um, the setting, our problem is limited to the problem that has clear answer. So maybe we wish to have a more wide applications. So that's the DeepSeek R1 stands for. They has a multiple process. So to solving one of the issue is quite easy to do that, which is the issue I just mentioned that um, they only train the DeepSeek R1 zero on a very limited type of the question. So if we wish to train it on a more general scenario, then we can go back to the like DPO simple RLHF things to do that using a traditional way. And the idea is that because DeepSeek R1 zero makes the model more intelligent, suppose we assume that we presume that it make, or we at least we hope it make the DeepSeek R1 zero model more intelligent. So then we go to the traditional training like DPO, LIHF, things like that. Because the base model is more intelligent, so maybe we can take advantage of this factor to make it generalize better. So although the general type of problem does not train, or it is unable to train in a more like DeepSeek R1 way, but still we hope that with a simple training it can understand and answer a wider range of problem. So that's a typical approach to do that. But DeepSeek R1 goes further. It actually has a four step of training. The first one is general SFT. Second one is like R1 zero. The third one is the one that I talk about, that to give a more generalized variation of question that it to train, and it can be mixed up with R1 zero training and like RHLF training. They can always use both use GRPO, and for the problem that has a clear way to verify, they give a reward like R1 zero. If it is not, they give a reward like other method. Then they all use GRPO as well. And finally, they do a distillation to make it to actually train control data set by the model that from the last three phase, and they control the data set, and by using SFT to train a smaller model, and it turns out the small model can be very intelligent after these steps. Also, that's the whole story about the DeepSeek R1. Okay, finally, it's a reference that we mentioned in the homework, the quantization. So if you click into the slides here, you will go to that page. Okay, so that's all for this week's lecture.